Ok, să începem cursul nostru de astăzi. So, last week we ended with this graph showing how to pick the quotient digits in the SRT radix 4 algorithm, right? So we discussed about the fact that you know, to keep the remainder within certain bounds, we have to put this constraint, namely that the partial remainder Ri must be smaller than 2/3 of B. B being, of course, the divisor. So yeah, so this is how we pick these quotient digits, and of course we want to favor the part where or the situation where the quotient digit is 0, right? And that's because it means better performance. But nonetheless, as radix 4 is all about, you know, putting two SRT steps in one step, two SRT radix 2 steps in one step, right? It's you'll get the job done in just four iterations, right? In 4 steps. If we are talking about, you know, 8-bit operands. So that was, you know, a quick reminder of our last week's discussion and where we left it. We left it here. So today we're going to pick up this and you know, exercise with 2 numbers how this algorithm works. So okay, the thing is here that, you know, it was pretty simple to decide just by looking at the Ri, the partial remainder, which is in register, it's held in register P. It's easy to pick the quotient digit, right, for radix 2, because for radix 2 we had, I don't know, maybe it was some weeks ago. Where is it? Yeah, it's this one, right? For radix 2, it's pretty simple, right? You have to decide, to check if you are between minus b divided by 2 and b divided by 2. So you have to be in this interval, right? So right now it's much more difficult. Okay, it's actually very difficult, and this problem is solved by a backtracking algorithm. We're not going to discuss about it. It's because we are not delving into these details and all that. So it's a backtracking algorithm which takes into account the value of b and of course the value of the partial remainder. Actually, we're interested in 6 bits from the partial remainder, such that we can see if we are, I don't know, between 1 divided by 6b and 1 divided by 4b, right? So we are within this interval or not. So when you put this together into this backtracking algorithm, the result is here, and I'm going to use these OneNote files starting this week. So when it's all said and done and the backtracking algorithm gives the result, you have this table, right? And this table should be read as follows. You take the value of b, but what it counts here, if we are to decide which interval are we dealing with, interval from Ri, we are interested in because b is on 8 bits, right? In the four leftmost bits. In other words, the most significant half, the left half of register B, right? And this value is, the value considered here is the one after the removal of the leading zeros. Okay, so it's when you are talking about B, register B, so it's like, I'm going to draw it here. So register B is like this, right? This is register B, okay? And we are taking, right, this is from position 7 to 0, it's on 8 bits, right? So it's 3 and 4 here. So this is B, okay? And of course, after shifting over zeros and removing the missing zeros, we will have 1 and, I don't know, whatever, yeah, something like this, right? So it starts with the 1. That's why we have a 0 here, an 8 here, right? Because it's the smallest b is 1 and then only zeros. So is 8, 9, and so on and so forth. Okay, so that's with b. And p, when we are talking about p, right, we should talk about, right, this is register p. It's on 9 bits, so it's from 8 to 0. All right, so we are interested in six such bits. So we are talking about, all right, from 3 to 8, right, and these bits are making the range of P in this table, right? In this table. But of note, we have to actually add one more bit here, right? Position 9, just because we need a sign bit, because we will make operations with 2b. We should subtract 2b or add 2b maybe. And we need an extra bit such that we can correctly perform operations with 2b as well. And that's because the equation of this algorithm, radix 4 algorithm, is given by, we wrote it last week as well. So Ri plus 1 is 4 Ri minus Qi b, where of course Qi can be within this interval. I mean, can take these values from the redundant set of digits. Now, I'll take this tablet next to me because it's easier for me to write this way. So, okay, Another thing that we should discuss here is, because the quotient will consist of digits from this redundant set, this one, right? Um, oh my God, this one, right? This set. So the problem is this: how should we interpret a number that is given as this one? For instance, if our quotient is, I don't know, 2, 1, or 0, like this, barred 2 and 1, right? What number is this? Well, it's this guy has the weight of 4, this guy 4 to the power of 0, this one 4 to the power of 1, this one 4 to the power of 2, and this one 4 to the power of 3. Okay, so what we have here is 2 times 4 to the power of 3 plus 0 times 4 to the power of 2, but that's 0, minus 2 times 4 to the power of 1 plus 1 times 4 to the power 0. So yeah, it's this guy is 1 plus this guy is minus 4, minus 2, 4, so it's minus 8, right? So it's 2 times 4, and then plus 4 to the power of 3, that's 2 to the power 6, so it's 64, 64 times 2, that's 128. So it's 128 minus 8, that's 120, plus 1 is 121. But of course, we cannot encode these digits with bits, right? Because in the binary system, we only have 0 and 1. We don't have minus 1, minus 2, and or 2, right? So we are forced to, to encode these redundant digits in binary. So what we do here is similar with what we did in Radix 2. So for Radix 2, of course, we have this redundant set, right? And so when we have something like this, it means one, this guy is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, right? So it's 1 times 2 to the power 3 minus 1, 2 to the power 1, and plus 1, 2 to the power 0, which is 1 minus 2, right? And plus 2 to the power 3, which is obviously 8. So is 8 minus 1, that's 7. Right? So the encoding for radix 2 goes like this. 0 up, 0 down. 1 is 1 up, 0 down. 1 minus 1 is 0 up, 1 down. Okay? And so 1, 0, 1 minus 1, 1 is encoded as, for 1, we have 1 up, 0 down. For 0, 0 up, 0 down. For minus 1, 0 up, 1 down. For 1, 1 up, 0 down. And so we subtract the part from below, right? This part from downstairs, we subtract it from what's upstairs. So it's 1, it's 0, and 1. And 0. So why is it's 5? So it's 8 minus 2 plus 1. So it's 5. Just a second. So that's 5. One zero 1 0 0 0 0 1 1 0. So it's like we have 9 minus 2, that's 7. Hey, yeah. Stupid me. Where's the, I don't know where's the eraser. Oh, it's here. Yeah. Yeah. I was so stupid not to remember how subtractions are made. So it's, you are borrowing 2 here, so it's 1, obviously. So it's 7. Yeah, but okay. I was thinking ahead, and of course I lost track of how to subtract. And ahead means let's encode this one, this number, right? So we want to encode it to encode this. And so for radix 4, we talked about radix 2. Let's talk about radix. Oh my God. Stroke already. Okay. Radix 4. We have this encoding. For minus 2, we have 0 0 upstairs, 1 0 downstairs. For minus 1, we have 0 0 upstairs, 0 1 downstairs. For 0, we have 0 0 upstairs and 0 0 downstairs. For 1, we have 0 1 upstairs, 0 0 downstairs. And for 2, we have 1 0 upstairs, 0, 0 downstairs. So 2, 0 to 1 minus 2, 1 is 2. So we have 1, 0 upstairs, 0, 0 downstairs, 0, 0, 0 upstairs, 0, 0 downstairs, minus 2. So it's 0, 0 upstairs, 1, 0 downstairs, and 0, 1 upstairs, 0, 0 downstairs. That's for 1. So we subtract what's downstairs from the upstairs part, and we have 1, 0, 0, 1, 1, 1, and 1. And that is, what is this thing? So it's 1 plus 8, that's 9. 9 plus, so it's 9 plus 16 plus 32. Actually, it's simpler if you just consider that I have here how many bits? 1, 2, 3, 4, 5, 6, 7. So what's the biggest number that you can represent on 7 bits? It's 127, right? And here what's missing is this bit and this bit, which means 6, right? So it's minus 6, so it's 121, which is true here. Like this. So it's actually 121, which is correct. Okay, good. Now, these are, of course, preliminaries for what's next. And what's next is that we want to actually divide these two numbers, namely, so this is an example. We divide let's take this example, 233 divided by 9, so it's 2 5, it's 5, of course. Come on. $53, and this is 5, 45, and that is, of course, it's 8 over here. So let's put 233 on bits. 233 is, so it's 1. If we subtract 128, right, so it's 5, it's 0, and is 1, 64, so it's 1 and 4, 32, that's 9. So 128, 64, 32, no 16, and then is 9. So this is 233, right? So let's draw the table. Yeah, I'm going to draw it. Although, can we make a table here? I guess we can. We can insert a table. How many? So I need 1, 2, 3, 4. Yeah, but yeah, I don't know. 4. Yeah, maybe like this. Okay. Let's move it. Like this. Right? No, it's better. I'm just losing time with this. So let's do it. Old school. Let's draw it. Okay, like this. This is the counter. This is register P. Like this. This is register A. Oh my God. This is so annoying. Okay, and this should be register B. Like this. Okay, good. Now, okay. Good. Now, this is the counter. Counter 2. This is register P. This is register A. And this is register B. Now, in register A, B, I'm going to put 9. Sorry. It's on 8 bits. Okay. Here is 233, which is 1, 1, 1, 0, 1, 0, 0, 1, right? In red, here I have 0, 0. In the register P, I have 10 zeros. Okay, and first I'm going to shift over 0 such that I arrive with this one, I'll arrive with this one at the most significant position in register B, so I eliminate all the leading zeros. So I'll have 0, 0, 0, 0, 1, 0, 0, 1. Then I'll have 4 zeros over here. And then 1, 0, 0, 1, 0, 1, 1, 1, and then only zeros. Okay. Good. Now, as I said, we are interested in this. This is only the sign part. So we are interested in 6 bits, but now we also have the sign part. So we're looking here, right? And this guy included, right? So 7 bits. 1, 2, 3, 4, 5, 6, 7. Okay? And we look at this table. Now, here, who is our B? We're looking at this 4 more significant bits from register B, and therefore B is 9, right? It's 1001, that's 9. So we are looking here in this table, right? Our B is 9, and if we are looking at this these 7 most significant bits from register P, this value is 1. So it's 0, 0, 0, and 1. That's 1. If we are looking here, where is 1? When B is 9, well, it should be somewhere here, right? Between -3 and 2. So if the range of P is 1, if P is, the range of P is 1, it's between -3 and 2, therefore the quotient digit is 0. Okay, so I'm looking at this table and decide that, you know, Q0 is 0, and then I shift it with 2 positions. I shift everything with 2 positions to the left. So I'll have here 0, 0, 0, 0, 1, 1, 1, right? 0, 1, 0, 0, 1, 0, 0, 0, 0, and now, because of this 0, I'll have 0, 0 upstairs, 0, 0 downstairs, just because of this guy. Okay, and now I'm over with this. Come on, dude. That's the color. Okay. Okay. Now I'm moving to the next step. I'm looking at these 7 bits, and what value do I have here? It's 7, right? It's 0, 0, and 1, 1, 1. 1, 1, 1, that's 7. So I'm going here. Where is 7? When B is 9, well, is here between 7 in this range, is in the range of 7 to 13, in which case Q, the quotient digit, is 2. So the quotient digit is 2. All right, so I make the shift, which is 0. This means that my Q1 is 2. Okay, so I shift 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0 upstairs, 0, 0 downstairs, and then 1, 0 upstairs, 0, 0 downstairs, because of this 2, right? This is the code for 2 over here. And because my equation is this, okay, when Qi is 2, it means that I have Ri plus 1 is 4Ri minus 2b. So I'll have to subtract 2b. Now, who is b? b is 1 on 9 bits, because on 10 bits actually, because p is on 10 bits. That's 0, 0, right? It has to be on the same number of bits as p, because we make additions and subtractions between b and p. So is b is this guy, right? 2b is this guy. Okay. Minus b would be, you know, we put it in 2's complement as minus. So it's 1, 1, 0, 1, 1, 0, 1, 1, 1 plus 1. That's 1 and 4 zeros. And 2b minus 2b is it's 1, 0, 1, 1, 0, and then 1s, plus 1, that's 1, and then only zeros. Okay, so we'll have to add 2b here. So we add 2b, which is 0, 1, 0, 0, 1, and then 5 zeros. The result is 1, 0, 0, 1, 0, 0, 0, 0, 0, and 1, right? Yeah. So, now something is wrong here. Yeah, stupid me again. So I said that it's minus 2b, and yet I added 2b. Damn it. So, oh my God. Something is wrong with me today. So, yeah. Okay. I said that we have to add minus 2b to subtract 2b, and yet I put 2b over there. So it's minus 2b, which is 1, is this value. 1, 0, 1, 1, 1, 0, 0, 0, 0, and 0. So it's 1 is 0, is 0, is 1, is 0, is 0, is 1, is 1, is 1, and 1. Yeah, that's the correct result. And of course, then we go on the next step. Okay. So that's step 1, 0. We are looking at these 7 guys. So what's the value here? Because I have here 1, 1, 1, 1, 0, 0, 1. Obviously, this is a negative number. So we interpret it as in 2's complement. Therefore, who is this guy? This is in 2's complement. So in 1's complement, that would be 1, 1, 1, 1, 0, 0, 0. So in sign magnitude, this should be 1, 0, 0, 1, 1, 1, which obviously is minus 7. Right? So we have to look into this table. So when b is 9, we have minus 7. Well, minus 7 is in this interval, minus 7, 3, which corresponds to a q being minus 1. All right? So we are going here. Our q is q2 is minus 1. Right? So we simply shift 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, then 0, 0 upstairs, 0, 0 downstairs, 1, 0 upstairs, 0, 0 downstairs. And because I have a minus 1, that's 0, the code is 0, 0 upstairs, 0, 1 downstairs. Okay, so I have this over here. Right? And according to the equation here, okay, if qi is minus 1, then ri plus 1 is 4ri plus b. So in this case, I'll have to add b, and b is 0, 0, 1, 0, 0, 1, and then 4 zeros. Okay, is this guy. Now we add, and we obtain 0, and 0, and 1, and 0, and 1, and 1, and 0, and 1, and 1, and 1. Now, I should take a look at these 7 bits. So who is this guy? 1, 1, 0, 1, 1, 1, 0, 1, 1, 0. Okay, this is in 2's complement, so in 1's complement, this is 1, 1, 1, 0, 1, 0, 1. And in sign magnitude, this is 1, 0, 0, 1, 0, 1, 0, which is minus 10. So this guy is minus 10. Now, when I look at the table, right, for b being 9, minus 10, where is minus 10? Well, it's between minus 14 and minus 8, right? So my q here in this step is minus 2. Okay, so come on. No. Apparently I clicked it correctly, although I got the impression that I didn't. Okay. So this is step 1, and Q3 is -2. Therefore, when we shift to the left with two positions, we have 1 0 1 0 1 1 0 1 0 1 1 0 1 0 0 1 0 and 0, then 0 0 0 up 0 0 upstairs, 0 0 downstairs, 1 0 upstairs, 0 0 downstairs, 0 0 upstairs, 0 1 downstairs, and then -2, which is 0 0 upstairs, 1 0 downstairs, obviously. So it's this guy, and this is the code for -2. And according to the equation, right, if right, Qi is -2, then I have Ri plus 1 is 4Ri plus 2b, right? So now I'll add 2b, and 2b is 0 1 0 0 1, and then 5 zeros. So this result is pretty interesting because it's 0 and 0 and 0 and 0 and 1 1 1 1 1 and 1. Now this should be the end of the algorithm, right? So we finished it. It's just that, okay, it's just that, you know, the remainder is negative, and this is incorrect, right? So we have this situation, as in the case of radix 2 SRT, we have this situation of a negative remainder, in which case we will make a correction step. The correction step consists of adding b to the partial remainder, the negative partial remainder. So, and of course, subtracting 1 from the quotient, which is equivalent with incrementing the register from downstairs, incrementing this value, actually adding 1 to the downstairs part of what's encoded for the quotient. So, as I said, we add, in the correction part, we add b. So b is 0 0 1 0 0 1 0 0 0 and 0, and the result is 0 0 0 0 0 0 0 1 0 and 0. Okay, so that's the corrected remainder, and of course I'll add a 1 to the downstairs part, so it would be 0 0, or we increment the register which holds this downstairs part of the quotient. In our case, it means 0, 0, 0, 0, 0, 1, 1, and because we increment this value, we have a 1 here as well. So, in the last step, we shift oh, come on. Damn it. This is so stupid. Okay. So we make this shift and conversion, meaning that we shift here with 4 positions to the right, the exact number of shifts that we made in the first step. So it's 0, 0, then 1, 2, 3, 4 zeros, and then 1, 0, 0, and 0. And here we subtract, right, the part from downstairs from the part from the upstairs part, so it's 1, and then 0, 0, 1, 1, and then this is 0, 0, and 0. And of course, the result is correct. Why? Because here I have 16 plus 9. 16 plus 9, that's 25. So it's 25 here. So this guy is 25. That's the quotient. It's 25, which is correct. Actually, the computer does not make these notes, right? It's for us humans to, you know, mark that this is, you know, the quotient, this is the remainder, and so on. Right, this is 8. Exactly as it should be, right? So we got the correct result. Now, okay, so I saved all these, and I'm going to go to a next the next section in our discussion, and I'll do this only for radix 2 because it's simpler. It's simpler than in the case of radix 4, and it has to be sufficient for our purposes. So it's 1 point, I don't know, 1 point, I don't remember, maybe 8 or something like this, is in this section we will talk about the hardware implementation of the SRT division. And we will come on. We will have the same preliminaries, namely we will use the Hayes hardware platform. Yes, and we will keep the notations, namely, even even if we discussed in terms of P registers P, A, and B, we'll scrap that and use the names, the Hayes names of the registers, namely A, Q, and M, right? Okay, so let's do this. I'm going to draw. Yeah, this is register P. This would be register A, and this would be register B, right? And we need a parallel adder, which I'm going to put right here. No, right here. Okay, like here or something. Okay, maybe a little bit up. Yeah, like this. And then also I have these buses. Just a sec. I have a stable tablet on my desk and the mouse and the keyboard also. So yeah, like this. These are the buses. And then this would be the control unit right here, and then I'll have this will be the counters. Okay, I'm going to put them right here. Come on. I'm going to put it here, right here, or something. Come on. Okay, like this. Okay, so I have register A, which is the equivalent of register P, but nonetheless. So I remind you that we are talking about radix 2, right? So it's radix 2 sorting. Okay, so this is A, this is Q, and this is M. We'll keep the notations from. So this is from rank 7 to 0, this is from rank 7 to 0, and this is from rank 0 to 8, right? So for radix 2, we are interested in A of 8, of 7, and of 6. And these three signals are fed to I don't like how I drew this. Okay. these are fed to the control unit. But first, let's talk about this. This is the parallel adder. On 9 bits. This is counter 1. This is counter 2. This, as I said, is the control unit. It has these external signals: begin, clock, reset, and end. When everything is finalized, these are external control signals. For register 1, and these are, of course, these are the buses. This is the out bus, and this is the in bus. Good. So okay, so let's start with the flow chart, because this we'll make these two in parallel. So the flow chart starts with this state: start, stop, and then if the begin signal is 0, then it stays here. If it's not, then it goes into this next step, which means something like this. Come on. Okay, so here what we do is that we reset register A. We well, I forget about something, and that is I forgot about, you know, the fact that when I encode the quotient, I need an upstairs and a downstairs part for radix 2. So I need an extra register for the downstairs part. So I'm going to name this as Q prime. Initially, this register should be on 0. So Q prime is also reset. We also reset counter 1 and counter 2. Okay, and at the same time we load the dividend in register Q from the in bus. Right? So we do all these things with the control signal C0. Okay, good. Now I'm going to draw right? Something from, because we, okay, we, no, 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 that's not, well, not the right color, obviously. So, come on, where is it? It's here, like this. So, this is so stupid. No. Like this. Something like this, where we, yeah, like this on 8 bits. So with C0, we dictate the loading of a queue with data from the inbus. We reset register A, we reset Q prime, sorry, I'll put it right here. No, I'll put it here, maybe it's better. So with C0, I reset counter 1, with C0 I reset counter 2. Okay, so that's the first step. And then I'll go to the next state. In the next state, I load register M. So I make this M is loaded from the inbus. Is actually register B. Okay, it's like this. With control signal C1. Okay, and then we perform that shifting over 0. So we are interested in the value of M of 7. If this value is 1, then we're done. But if it's 0, then we'll have to, do something about it, and we'll have to shift. So then come back here, right? So it's something like this. Now, what we do here is that we shift through registers M concatenated with Q concatenated with A, and we increment the counter 1. So in A concatenated with Q concatenated with M from 7 to 1 down to 1, we put what was previously in A from 7 to 0 concatenated with Q and concatenated with the entire M. And then, yeah, I should make a bigger square rectangle here. We put in this position in M of 0, right? When we shift, we will take a 0 over here. So M of 0 will be 0. At the same time, we increment the counter 1. Okay, good. Now, all of these are dictated by control signal C2, sorry. Okay, so with C2, I will, first I'll increment count 1. But what we need here is a chain of registers from M through Q and A. And that's why we need to, make this chain here. Like this. Well, we need to do the same thing between Q of 0 and M of 7, but the problem here is that this chain has to be interrupted for when we shift through Q concatenated with A only, and that is when we execute the algorithm. So sometimes we need to break this chain. So that's why we put here a multiplexer like this, such that sometimes we take another value from here, right? And this is the control signal. Remember what a multiplexer is. So we have 0, 1. This is I1, input 1, input 2, and this is the output, right? And this is the control signal. So O is I1 if C is 0, and I2 if C is 1. So I control with this control bit, with this guy, I control the multiplexer. I control the output, whether it's I send to the output I send M of 7 or something else. Okay, so good. Good. So that's it. Oh yeah, and I'll put C2 here because when C2 is 1, I need this chain, and C2 also is taken as the clock for, I don't like how this was this. Okay, C2 is also, as I said, is the clock for these flip-flops from registers A and Q and M. So when C2 is active, it dictates the shifting through all these registers. Okay, so yeah, that's C2. And then we move in the flow chart, and after doing these preliminaries, we go to the algorithm, the actual algorithm. So in this algorithm, we test the three values, signal values, these three, A from 8, A of 8, 7, and 6, obviously. Now I need these three values to arrive here at the control unit. Okay. So it's like this, right? These three signals arrive here, and the control unit acts according to the value of these signals. And as I said, accordingly, we have three situations. The situation pertaining to, let's say, 1, right? Where the value of these three bits are 0, 0, 1, 0, 1, 0, or 0, 1, 1. Remember, they should be different. I mean, these bits have to be different. I mean, we cannot have three identical values, like 0, 0, 0, and 1, 1, 1. And they should start with a 0, okay? Meaning that it is positive. Now, for the situation of -1, we have 1, 0, 0, 1, 0, 1, and 1, 1, 0, right? And of course, I have this 0 branch where we have 0, 0, 0, and 1, 1, 1 for these three values. So these are the cases. And okay, let's talk about it a little bit. I'm going to erase this because I need this space over here, so yeah, write it. Like this. Okay. Come on. Like this. Oh, Jesus. And this one over here. Yeah, that's good. Good. So what will happen here? Well, we shift through registers A concatenated with Q, right? We also shift Q prime. We enter in Q0 and Q prime of 0, we enter the encoding of the quotient digit, and we count up. No, we do not count up. Here. Yeah, and then maybe we add or we subtract something. So that's what we'll do over here. So first I'm going to write here that A of that's the shift. In A complete, A concatenated with Q from 7 to 1, I'll put what was before in A of 7 to 0 concatenated with the entire Q. In A of in Q of 0, I put 1, right? And then in Q from Q prime from 7 to 1, I put what was before in Q of 6 down to 0, and in Q of Q prime of 0, I put 0. And then that's it. So you see, it's 1 upstairs, 0 downstairs. So it's the same thing here. It's the only thing that differs is what we put in Q of 0 and in Q prime of 0. That's the thing. That's what differs here. Okay. So I write the same thing. So A concatenated with Q from 7 to 1 is A from 7 down to 0 concatenated with Q. In Q of 0, in this case, I'll put 0. And then in Q prime from 7 to 1, I'll put Q prime, what was in Q prime from 6 to 0. And in Q prime of 0, I'll put 1 this time. So you see, I have to control what bits are taken here in Q prime of 0 and in Q of 0. Obviously, in Q of 0 comes this signal, right? The other entry in the multiplexer. So I'm going to, I'm going to put here signal C3 for the shift. So I need C3 all over in all these three cases, because I activate C3 because I shift through registers A, Q, and Q prime in this case, right? So I need this control signal, but I also need C4 here. I activate C4 here because it's 1 upstairs, so this guy is C4. And I activate C5 here when it's 1 in Q prime of 0. So it's C5 here, right? And that's it. That's here in this state. I'll do A concatenated with Q from 7 to 1. I put what was before in A of 7 to 0 concatenated with Q, and then in Q of 0 I take 0. In Q prime from 7 to 1 I'll put Q prime, what was before in Q prime, from 6 to 0, and in Q prime of 0 I put 0. So no need to activate C4 or C5 because it's 0, 0. They should be inactive here. Okay, so after these states, I mean after this one, I have to, after the shift, I have to subtract, and here I have to add, obviously. So you see, I'm going to put something here like this. Sorry. Come on. Let's take it like this, and like this. Deci, aici, so here we have we make this subtraction, right, between A and M. So A would be A minus M, and here we do A plus M, right? So we know according to the algorithm. And so here I'll activate control signal C4 here as well. We know that this means that we actually load in the destination register, namely register A, what comes from the output of the parallel adder. Um, so additionally, when we do subtraction, we have to activate another signal, in this case C5, such that the operand is negated. So, but another thing here is that we have to understand that we don't do addition or subtraction only between A and M. We also need to do something between, namely subtraction. We have to subtract Q prime from Q to convert the quotient in binary. So we need multiplexers here as well, because you see, I need to do something like this. Sometimes I do addition. I'll use the adder for adding M to A. Sometimes I need to use the adder to make additions, subtractions between Q and Q prime. So I'll do something like this. Okay. Okay. Here, it's a multiplexer, right? With 9-bit signals. Right, and here, okay, no. Like this. And you see, I need something like this. Okay, right, so like this, and like this. Come on. Right, so we have 9 bits from here. Obviously, 8Q is on 8 bits, but I'm appending a 0 bit here, so I'll have 9 bits over here. And I'll also have register A. Oh my God, this is so annoying. So you see, okay, at some point I'll have to put the result here from the remainder on the out bus, right? And yeah, but I also, God. Okay, so it's something like this. We take this, we take these 9 bits and only 8 bits, right? We ignore the most significant one when we put the information on the out bus. Okay, so we have this here. We have 9 bits from here. And yeah, something is something that I don't like here. Okay. So yeah, let's do it like this. So as I said, we take 9 bits here. Okay. Here I'll have a multiplexer. Normally, we take the operand on the 0 branch, but sometimes, you know, I'll put something from here as well. So because I need to make subtractions between Q and Q prime. So Q prime should be an operand here as well. Okay, like this. These are 9 bits because we also append here a 0 to these 8 bits coming from here. Okay, and yeah, actually that's a mistake here. Yeah, it's a mistake here, but I'll correct it. Yeah. Everything is okay. It's just that I forgot about, yeah, and the heck is going on here? Come on, dude. Go there. Yeah. Come on. Okay. So we take 8 bits from this register. We also append a 0 and we'll have 9 bits over here. So yeah, I forgot here about this word gate, this XOR word gate, right? And the signal, which will be a control signal. I don't know. I know which one. This C5, right? This would be signal C5. Right, and C4, so I also need this guy over here. Okay. Here a control bit as well. So I'll put the result in 2 places. First, now I did something wrong here. I did something wrong. Yeah. Yeah. So I'll erase it. No biggie. Yeah. Yeah, because this that the direction here is from Q to the multiplexer, right? So yeah, unfortunately I don't have the space to, yeah, let's see. So I'll put a demultiplexer here. So when it's on the 0 branch, the result on 9 bits will go to register A. Otherwise, we'll go to register Q. So I'll just draw. Let's see this and this. No, it's this. Okay, so it's on 9 bits, and we need to go like this. Why? This is, as I said, is stupid, very stupid. Okay, so let me fix it like this, like this. Okay, and then I'll draw this line over here, something like this. No, no. Okay. Okay, something like this. And obviously like this. So yeah, yeah. So let me, and just a second. I'll finish this, and then that's it for today. But I just want to leave this drawing in a good shape. So you know, it's going from here. Yeah. So yeah, I'm going to do this like this. And yeah, so on this path, Q is loaded with information, And here, ah, I hate it. And here, okay, all right. So something like this. Okay. Like this. Good. So it's like this. Right? So, and then, because these are 8 bits, here I'll append 1 here, a 0. Right? So this is how we do additions and subtractions, and now we have the entire infrastructure. Obviously, we have not finished it. We have not finished the flow chart, and you know, with the control signals and all that. Yeah, we'll need this. For instance, this signal is needed such that we put the contents of register Q on the out bus. Let me finish this as well, because this is important, such that next week we will pick things from a correct and complete, you know, drawing and hardware diagram. Okay, okay, just go there. All right. All right. So yeah, so this these signals are going to from register Q to the outside, whether we are talking about this multiplexer, which directs the signals towards the inputs of the parallel adder, or we are talking about the outbus. Okay, so now everything is in order. We'll finish this next week. Okay, we'll pick things where we left them. Yeah. Next week we have this drawing and we'll finish it. Yeah. So right now I'll finish my stream on YouTube and go to Discord. If you have questions, I'll be happy to answer them. Okay. So let's hear each other on Discord after this.